I can read it upside down.
Your thing?
Yeah.
How about I just step back here?
Counting us down? Hi, everyone. Science Sunday, March 20th of 22, and we even have some science fans in the audience, so thank you very much. We're actually talking to more than just chairs today, and that's a great start, and hope the rest of you have opportunity to get in and participate in a Science Sunday in the next short while as well, too. Today, Scott's going to be talking about the general theory of relativity, and I wore my one of my Einstein t-shirts here. Scott, you could...
That is so awesome, and he's having fun on a bicycle.
Right.
What's it say here? Creativity is intelligence having fun.
Right. And
that's great.
I try to live up to that remark, although I'm probably missing in both creativity and intelligence. But. So, I did want to announce that, more people coming in, great. That 2 weeks from today, April 3rd, is a topic I'm interested in because I've got about a 5.5-month-old granddaughter, and her mother, my daughter, Jessica, sent me this book, 1,000 Days of Wonder, and it's an actual scientist who's lived in England and Australia, chronicling his daughter's developing mind. So like all scientists, he got to do what we all would love to do, which is mess around with your kids, right? He was messing around with his daughter and giving her all sorts of tests, cognitive tests, putting little dabs of paint on her nose and seeing how she reacted and theorizing about it. So I do want to talk about that and the development of the intellectual brain, how that happens in infants before they're even born, and what goes on in the first few years of their life. And I also was asked by Carrie to talk about artistic development in children, and I think I'm going to ask her to come in and talk for a few minutes about that as well. So I'm pretty excited. I wanted to have you think of two mental images about that. One is a flower just starting to unbud, and you've seen those slow motion pictures of a flower unfolding from a bud out into a beautiful flower. And that's one image of maybe brain growth and brain development. You know, we can kind of intellectualize or think of it that way. And another way is like if you'd seen a time-lapse movie film of a city growing and a city just changing from like Manhattan from in 1918 to how it is nowadays, and just see the growth and buildings going up and moving and changing and so on. And that's another way to think about brain development. And I wanted to maybe plant both of those pictures in your mind and to think about and how they do maybe describe how they're similar to actual brain development and maybe how they're different as well too. So I'm making a plea especially to parents, grandparents, and those involved with young children. Come to Science Sunday in 2 weeks. We're discussing what science knows about the development of the brain. So without any further ado, and we're sorry for starting a little late, we have to wait and let the church service plan a little bit of time to get the songs recorded for next week's church service. That's why we're starting a little bit late. We come in here about 5 minutes ago now and started scurrying around like little beavers getting things done. So we're starting a little bit late right now, but I want to have Scott jump into his topic about Albert Einstein and general relativity.
Thanks, Mike.
All right.
Good afternoon, science lovers. It's great to be here again. I've given 2 prior lectures on the theory of relativity. That was covering what's known as special relativity. Einstein didn't call that in 1905 when he produced some papers that helped describe the way nature works in a more accurate way than Isaac Newton did a couple hundred or 300 years previously. Einstein didn't call his first foray into understanding how the universe works vis-a-vis speeds and motion and energy. He did not call that the special theory of relativity. He actually wanted to call it, I believe, this the theory of constants or theory of consistency. I may have that slightly wrong, but his main point was there were things, or theory of invariance, I think. There were things in nature that were absolutely invariant no matter what. And one of the most fundamental things that was invariant were the laws of nature themselves. So he looked at Maxwell's equations, which describe the way electric and magnetic fields behave and their relationship to one another, and he deduced from a careful thought, a series of careful thoughts about Maxwell's equations, that the speed of light would be one of those constant rules of nature. And at the time, most scientists would have disagreed with him. Turns out Einstein was correct. And simply by taking that fact of nature into account, he deduced all kinds of implications about the relative speeds of ticking clocks and rulers that measure distances as compared between different reference frames. Now, this idea of relativity wasn't necessarily new. Even before Isaac Newton, Galileo had recognized a category of relativistic observations. So the classic notion is that he was thinking about dropping a cannonball, or maybe a ball of a cork or something that wouldn't hurt the people or the ship, but dropping a heavy object off of the tall mast of a ship, and it would fall down. And we talked about this a couple of Sundays ago. If you're standing on the deck of the ship and you see this falling object, you will see it falling straight down from the top of the mast to the deck of the ship. But if you're standing on the shore or perhaps on another ship moving at a different speed relative to the one we're dropping the cannonball from, you might see the cannonball, or you will see the cannonball, follow this arc that's depicted in this motion graphic here. So 2 different observers would disagree about the trajectory of a falling object. And this was long before Einstein. And, if you're standing on the ship that has the dropping cannonball and you're moving along with it, then the total length, the total path length described by that cannonball is just the height of the mast. But if you're on, this is the picture of if you're on the ship, if you're watching a moving ship that is no longer stationary with respect to you, you'll see the cannonball follow this arcing trajectory. And then if you really get moving fast, you'll see a much longer arc that the cannonball describes as it falls towards the deck. And if you're into calculus and mathematics, you can write a formula for this arc length observed by different observers. And you'll notice that nowhere in this formula is the letter c. The letter c is a numeric representation of the speed of light that shows up again and again in Einstein's relativity. But Galileo had no notion whatsoever that the speed of light was special. So even in Galileo's time, according to the consideration of logic and observation of the way nature works, there were some quantities, some processes in nature that differed depending upon your relative state of motion. And we covered a lot of that last time. We also talked about the twin paradox, so-called paradox. Nature does not have any real paradoxes. It doesn't allow them. There's only one set of the rules of nature, and they're never violated. If we have our mathematical representations of the laws of nature, And those mathematical terms may conflict with each other. Well, the problem's with our models, not with the way nature behaves. So there's no real paradoxes in nature. But the twin paradox talked about one twin stays stationary on a planet, another twin zooms away towards a distant star, and then comes back again. And according to the notion that all things in physics, all measurements should be relative to your speed, why is it that the person in the rocket ship can't presume that the twin on a planet Earth, say, moved away and then came back? So that's where the paradox comes in. The motion between the two observers is not symmetrical. And indeed, it's this lack of symmetrical motion that explains the real effect of the twin paradox. And we talked about that quite a bit, I believe, in the first episode of my series on relativity. So I'm not going to go through all of the explanation again. I do want you to pay attention to this strange line diagram with the big triangle in it. It indicates the path of the rocket along the red and then the green line through space-time. The yellow dotted line is the path that a light beam would take through space, which is distance along the x-axis, and then through time, which is represented on the same scale of units by multiplying time times the speed of light. A speed is a distance divided by time. So if you multiply a distance divided by time, the units of measure become nothing other than distance. So the two axes on this graph are both units of distance, but to translate time into distance, you have to multiply an interval of time by the speed of light, by a conversion factor. And that'll be really important in a few minutes. You can come up, using special relativity, you can come up with this formula about the total interval between space-time events. It's the change in time multiplied by the speed of light and the change in distance, and both of those squared, and then you take the square root of that, similar to the Pythagorean theorem. So all of that, everything we talked about in the past 2 months was consistent with something called Minkowski spacetime. Hermann Minkowski was a teacher of Einstein's when Einstein was in college and later became a collaborator. And one of the insights that Hermann Minkowski had after reading Einstein's papers about the special theory of relativity, again, it wasn't called special relativity back then. I'll get to that in a minute. But one of the insights that Hermann Minkowski had was that you could represent some of the phenomena that Einstein perceived with diagrams that are geometric, and you can create an axis that corresponds to space and an axis that corresponds to time. And then you can start drawing out geometric figures that help explain some of the strangeness of special relativity. And this is called Minkowski spacetime. One of the key and the most important characteristic of Minkowski spacetime for today's purposes is that it was flat. It was a flat geometry, similar to Euclidean geometry, but with this extra conversion between time and space thrown in. Remember that multiplicative factor of the speed of light to change intervals in time into intervals of distance. And then we've got the twin paradox, and I don't think I'm going to go through that in any more detail again this week. Now we're going to start talking about general relativity. That was a 5 or 6 minute crash course in special relativity. I hope you all perfectly comprehend that. If not, go back and look at some of the prior videos, and there's many more videos available online, many books available to help you understand special relativity. But let's move beyond that now. Okay, we're going to take a deep breath because things are going to get pretty weird. So, let's say you're moving in a circle. Well, you can approximate a circle by inscribing within that circle a kind of polygon. So here are a series of straight paths through space-time, as it were, etched in around the curved circumference of a continuously variable trajectory. And you can imagine that as you multiply these straight paths, and you have a ever larger number of little line segments in your polygon, your polygon will come to approximate ever more closely your literal path through a continuously curved space-time. So one of the ways you can arrive at some of the consequences of general relativity is by considering special relativity as being locally relevant, but slowly transitioning in terms of literally the geometry of space-time. We're no longer talking about a single flat space-time, but a series of minusculely sized flat space-times stitched together into a curvilinear version of space-time.
Isn't this how the Greeks originally developed the circumference of a circle? And
Yeah, it's one way.
Developed pi and so on?
Mm-hmm. Yeah, you can take the ratio of the chord length compared to the length of the each segment in a polygon and come up with an estimate of pi. Funny you should mention pi. You know, it was just Pi Day.
It was Pi Day, right.
Yeah, Dave and I were going to go out. Dave's in the audience, my husband. Great to see him here. But we were going to go out and have pizza pie for Pi Day, but we ended up having a family obligation. But I think maybe we'll do that next year. We'll have Pizza Pi Day. We'll have a little party. Anyway, I'm going to talk more about pi later. Little primer. So if you want to grab a snack, it's lunchtime. Feel free. We'll talk more about pi in a moment. But in any case, you can stitch together these minusculely sized, straight, flat regions of space-time, and by skewing them with regard to each other slightly, you can come up with as continuous a curved space-time as you wish. And here's another thing that's a piece of perhaps deeper insight than you might have thought of, just trying to follow along with what I'm saying. Remember that the twin paradox, the change in the relative rates of clocks and the measurements of rulers, happen because there is a lack of symmetry between the reference frame of one observer compared to the other. That moving twin must exist in two different inertial reference frames. Must exist in at least two different inertial frames in order for that twin or that clock or even the information about that clock to be sent back to the twin on Earth. So some of the strangeness of special relativity only becomes evident because we start mixing multiple frames of reference that are not identical. As long as you're in the same frame of reference, any experiment you conduct within your frame of reference will give you consistent, non-paradoxical results. But once you start comparing frames of reference between frames that are not in uniform motion with respect to each other, you have to start taking into account that you've got these sudden changes around this polygon of the curved path. And again, if it's a smooth trajectory you're arcing through in terms of your acceleration, remember, moving in a curved path is a kind of acceleration. That's why you feel a force when you're going around a curve in your automobile. But these curved paths through space-time are by definition non-inertial. When you say inertial reference frame, you mean constant state of motion in a constant direction. And when you're changing direction or speed, you're in non-inertial motion. And you start having to stitch together this idea of a non-inertial frame by taking infinitesimal slices of inertial reference frame and knitting them together into the fabric of a curved space-time. Now, the next important thing is what Albert Einstein considered the greatest thought in his life. And he was a smart man, and he had an uncountable number of great thoughts, from the photoelectric effect to the existence of atoms being implicated in what's known as Brownian motion. He was not just a scientist who thought about relativity. He extended his insights and his phenomenal capability for imagining things and having what he called thought experiments or Gedanken experiments into other realms. But his most cherished thought experiment that gave him the deepest insight of any that he had, according to himself, was this notion that if you're at rest on the surface of the Earth and you drop an object, that object will accelerate down towards Earth. the object experiences a force and an acceleration. The force due to gravity is equal to the mass of the Earth, which is the giant M in this equation, and the mass of the projectile that you're dropping. Could be a spoon or a cannonball or a feather, divided by the square of the distance separating the center of gravity of that feather from the center of gravity of Earth. So pretty simple geometric equation. The G is just a conversion factor to make all the units of measure come out. It's called Newton's gravitational constant. But there's another equation that we know about from Newton that says that the force on an object is proportional to its mass times its acceleration. Well, recognize that both of these are equations about force on what's called a test mass, be it a feather or a cannonball. So the same feather or the same cannonball can experience a force, whether it's accelerating or whether it's moving under the influence of gravity. And this implies that the acceleration, you can play with these two equations, set them equal to one another, and solve for acceleration. And you end up finding that the acceleration of a falling object has nothing to do with the mass of the object that's falling. Whether you drop a feather or a hammer, the acceleration due to gravity is constant, which is completely counterintuitive, because if you go outside right now and you drop a feather and a hammer, I can guarantee you that the hammer will hit the ground first. What you need to do is you need to do this experiment on the moon. And when you do this experiment on the moon, which was actually done, you'll see here, I think it's in the, if you can zoom in on this slide, the astronaut's right hand, which is on the left side of this animation for you. The astronaut's right hand has a hammer that's being dropped, and from his left hand he drops a feather. And you can see this happened on the moon. You can see that the hammer and the feather hit the surface of the moon at the same time, because there's no oxygen to impede or add any buoyancy to the progression of the feather as it plummets towards the moon. So this and many other experiments have been undertaken in order to prove that what's called gravitational mass, which is in Newton's theory of gravity, and inertial mass, which is in Newton's idea that force is equal to mass times acceleration, those two mass measurements or mass quantities are exactly the same. There have been experiments that are much more sensitive than just watching a video of a hammer and a feather on the moon. There have been sensitive experiments done to show that the agreement between the amount of gravitational charge in a quantity of matter and its resistance to motion are identical things to something like 8 decimal points. And it's really hard to do these experiments because in the context of the universe and the forces of the universe, the force of gravity is relatively weak. So trying to do this with a couple of different test masses in a laboratory tends to be difficult experimentally.
Can you repeat what are the two things that are exactly like the 8 decimal places? I thought I had it, and then I thought it...
Okay, kind of, yeah. So you can think of the gravitational effects of a clump of matter sitting in space as being a kind of charge, because it induces motion in other pieces of matter within space. So just like a given electrical object subject to electrical forces can have a varying electric charge. You can have a metal ball that has 0 charge. You can have a metal ball that has negative charge. You can have a metal ball that has positive charge, and that charge amount can vary. That's the amount of charge on a mass. Well, you can think of the gravitational potential of a mass sitting in space as its gravitational charge. It's a separate thing. It's the amount of gravity effect that this particular mass has. But there are strange things about the way gravity works compared to the other forces of nature, such as the fact that there's no such thing as negative mass. So you can never have a negative gravitational charge. And even more peculiarly, the the effect of acceleration, the tendency of a massive object to resist acceleration, is quantifiable. And that quantity we call its inertial mass. It's the measure of the tendency of an object to resist acceleration. And there's no a priori reason in the amazing universe we live in to presume that the amount of gravitational charge on a mass is identical to the resistance of acceleration of a mass, that those measurements of those responses of the mass to different contexts would be identical. But they are. And Einstein was one of the first people, if not the first human being, to recognize the profound implications of this identicalness. And one of the ways that he characterized this was in an elevator sitting on Earth, not moving, or a box sitting on Earth, not moving. And within this box, you would discover that an object dropped has a certain acceleration. It experiences a gravitational force. Conversely, you can put this box in a rocket ship or a spaceship that is propelled through space with a given acceleration. So it's not just moving through space at a constant velocity, it's accelerating through space. It can either be on a curved trajectory, like a spinning space station, or it can be in a rectilinear, or it can be in a linear kind of acceleration, such as a spaceship that is propelling itself. But if you're in this box, in this space station or spaceship, and you're accelerating, you will feel something identical to a force of gravity. So the acceleration force and the gravity force are so intimately connected that it is not only difficult to separate one from the other. Einstein said, why bother? They are the same thing. And this had some really profound implications for his subsequent thinking about the laws of physics occurring in accelerated reference frames. Remember, special relativity was a special case about motion through an inertial reference frame. To consider the more general case of accelerated motion, he had to start thinking about curved geometry. And also he started thinking about the relationship between acceleration forces and the force of gravity. And it turns out that what he ended up doing was developing a theory for the way gravity acts that was purely based on the geometry of space-time. So here's once again that circle with different chords on it, and or a polygon inscribed within it. And then also an image of something you've probably seen before. This is a mass. Here it's represented by an orange dot. You can think of it as a star, and then there's another orange dot circling around the star because of gravity. But the way Einstein thought of it was, these are just stitched together, microscopic-sized inertial reference frames that, when they're stitched together, make a curved space-time. And the curved space-time, once you work out the equations of motion for the curved space-time, they tend to be, to a first approximation, identical to what Isaac Newton found. So instead of talking about forces, mysterious forces acting over a distance, Einstein said, no, there's no mysterious force. It's just that matter and energy, remember, E equals mc squared, matter and energy tells space how to bend, and bent space-time tells space-time how to bend, and bent space-time tells matter how to move. This was a famous statement made by John Archibald Wheeler, one of the mid to late 20th century's sages when it comes to understanding and teaching Einstein's theory of gravity. So if we can start viewing space-time as being warped, what does that mean? What are some of the implications? Well, one of the implications, the first one that Einstein thought of, I'm not sure what he thought of first, but one of the first published implications is that the image of a star from behind the sun should be warped as it follows a trajectory that's curved through space-time. Now, initially, in 15, when he made his prediction of the deflection of starlight, his prediction agreed with Newton's prediction. But then he thought about it, and this is really subtle, and I want you to try and wrap your mind around it. It took me a long time to try and get an approximation to an intuitive view of this. If you're bending space and time, remember that diagram where the quantity of time is multiplied by the speed of light, whereas the distance measure is just a distance measure. The implication of that is that a tiny, tiny deviation in an interval of time leads to a tremendous difference in the total interval of space-time. The same amount of deviation in a distance coordinate is just a tiny deviation, right? So a deviation of a slower clock creates a bigger effect than the same change applied to, the same magnitude of change applied to a unit of distance, the length of a meter stick. And the implication of this is profound enough that I'm going to reiterate it in a moment. But for now, recognize that Newton's theory of gravity really only takes into account the warping of the time effect due to gravity. And if you're talking about a light beam, which is moving at the speed of light, so the distance it covers is in some units of measure, the distance it covers in a unit of time is equal to the amount of time elapsed during that same interval. So the speed of light is special. It moves 1 unit of time per unit of space, 1 light year per year, 1 light second per second, 1 light nanosecond per nanosecond, 1 light decade per decade. That's special to the speed of light, and it makes it an equivalent effect between the warping of space and the warping of time for a light beam. So when Einstein first calculated the effects of the warping of space-time, he did not correctly take into account the warping factor of space, which would be most evident on things like light beams, things that move at or very near the speed of light. So he ended up doubling his prediction for the deflection of the image of a star as it grazed the sun. So during a solar eclipse, when you can see the stars behind the sun, Sir Arthur Eddington in 1919, I think, measured the deflection in the angle of a star beam grazing the vicinity of the sun, and found that it was indeed twice what Isaac Newton had predicted, and consistent with what Einstein predicted. I promised pie. I hope you've gotten your snack or your lunch already.
Yeah. I was just thinking about that, and are they doing that because they measure the time the sun is moving during this eclipse, and you're seeing the star as it's on one side of the sun, and then you know the speed that the sun is moving, and it should be able to be seen on the other side of the sun? Does it?
Yeah, kind of. The motion of the sun through space, which physicists call its proper motion. So the proper motion of the sun through space is fairly negligible. In fact, the calculation of the deflection of a beam of starlight can completely ignore the motion of the sun. So the motion of the sun is not the relevant thing. It's the gravity of the sun that's relevant. And we can say, you know, the constellation Orion, for example, is not visible during the summer. I should choose a zodiac constellation because that's in the path of the sun. So the constellation, Cancer is not visible during the summer. I may have that backwards. But in any case, there's a constellation. Any given constellation, as the seasons change, as the Earth moves around the sun, that constellation will be viewed from our perspective as being behind the sun, and our daylight sky will wash out any view of those distant stars. But if you have an eclipse of the sun, then suddenly you can see those stars, and you know where they are in space, right? The stars aren't moving fast enough. Their proper motion is so tiny that we don't expect the star in the constellation Orion to be different located different relative to the coordinate system of the sky. We don't expect that coordinate to change between summer and winter. But if suddenly that star is right behind the sun, or just our vision of it just grazes the sun, that light beam will be deflected.
That's where I didn't know if they were measuring, how do you know where the star is supposed to be, but stars, you generally know their position in the sky. And this is at one point where the sun happens to be
Right.
so close to them that it's deflecting their light, and you can measure where you think it should be, but it's
Right.
off of that deflection.
Exactly, yeah, and that deflection ended up being twice what Newton predicted it would be, just naively. And I'll talk more about the relationship between space and time and the conversion factor here in a minute. But first, I want to talk about the fact that pi, there was some legislature in the United States, some state legislature a while back that said pi must be equal to 3. We are tired of our students having to learn all these decimals just to deal with circles and triangles. Gosh darn it, by official decree, pi is equal to 3. Do you remember that? Have you ever heard of that?
I don't know. I don't put it past them, though.
Yeah, well, it happened. So, you probably recognize that that's ridiculous, because pi is pi. It's the ratio of the diameter of a circle to its circumference. In this little equation here, circumference is equal to pi times the diameter. That's what you learned in high school or junior high. I don't know when they teach it these days, probably in kindergarten. But, the circumference of a circle is pi times its diameter, and pi can be calculated by measuring this ratio, just like you were saying earlier with the ancient Egyptians and carving the triangle or the circle up into a series of triangles and whatnot.
They did polygons that got more and more facets to it,
Right.
inside and outside, so you can
Zoom
come
in on
at it.
Yeah,
Right.
That's awesome. So, it's a universal truth that pi is equal to pi, 3.141592665, and so on, ad infinitum. Except if you're in curved space-time. Suddenly, the value of pi changes. So, I don't know, the state of Ohio or whatever state it was, if that state were to transport itself to the vicinity of a black hole or some place with a really strong gravitational field, well, then maybe they could get a pi equal to 3.
For a few seconds, maybe, or milliseconds,
Yeah.
and then they'd be sucked into the black hole.
Right. So you can picture, this rubber sheet analogy. That's what it's called. You get a heavy ball sitting on a rubber sheet that's got grid lines painted on it, and you can imagine this warping of this sheet. And I'm going to use that picture a couple times throughout today's talk. And by the way, there's no clock here anymore, so I'm probably going to talk for 3 hours. I hope your afternoon is not busy. In any case, instead of thinking about a warped rubber sheet, you can think about the volume around a gravitating object, like around the Earth, being warped and stretched, kind of more like this picture rather than the rubber sheet picture. And then here's a diagram of the rubber sheet, because it's much easier to visualize, and it has some real utility as an analogy, right? We can think about it this way, and we can think about it productively using this rubber sheet analogy. So if you could zoom in, if our AV person can help us emphasize this slide for a moment. So you can see that in one of these diagrams, the sun makes a little divot in space-time. And someday, after a few billion years, our sun will be replaced, or all that will remain of it, more precisely, will be the core, the hot core of the sun, slowly cooling down, no longer performing nuclear fusion. And that'll be a white dwarf star, which is about the size of the planet Earth. But most of the mass in today's sun will be compressed into a little ball about the size of Earth, rather than thousands of times the diameter of Earth. And so the gravitational field we would expect, or the gravitational effect we would expect around a white dwarf would be much more intense. You see that the divot pulls down further in that rubber sheet. And then we have a neutron star, which stars heavier than our sun may eventually end up as, and we know neutron stars exist from astronomical observations. But a neutron star has such powerful gravity that the warping of space-time is extreme. And then finally, a black hole is where the warping of space-time becomes infinitely steep, or becomes a vertical line. So in all these other examples, even though these diagrams may not show it as accurately as I would wish, in the sun view, in the white dwarf view, in the neutron star view, there's a slight slope to the edges of that divot. It's not completely vertical. But with a black hole, you reach a point where the slope, the curvature of space-time becomes vertical. And that means that not even light can escape the gravitational effects. The warping is so strong that a light beam can't even come out of that tunnel. But there's another interesting thing to think about. Thanks for zooming in. You can go back to the regular slides now. There's another set of implications about that. Oh, black holes. Slight diversion. This is an artist's impression of a black hole that's siphoning material off of a blue giant star, and the material swirls around the black hole, and electrons and protons get stripped out of atoms and create these electric and magnetic fields in this swirling disk. And because of those fields, some of the material gets ejected out. The spinning axis, the north and south spinning axis of a spinning black hole, or the material that's spinning into a black hole, and you get these cosmological jets. So amazing dynamos. And then you can pause this video later and come back to it if you'd wish. Here's kind of the anatomy of a black hole. I know a lot of people are interested in these creatures, these behemoths, these eater of worlds. And then in the little animation down there, you can see what it would look like if the Milky Way galaxy, or the band of a galaxy, the image of a distant galaxy, was, because of perspectives and whatnot, moving across or behind the location of a black hole. The black hole warps the image of the paths of light beams. And that's one of the reasons why you see in the orange picture, the schematic diagram of a black hole, the orange band on top and on bottom are actually reflections of the distant far end of the ring around it. But because of the warping of space-time, you can see the things behind the black hole. It's crazy. Anyway, if you're interested in this, you can come back and pause this video. Could you zoom? Yeah, could you zoom in on this? Yeah, you did. Thank you. So we can continue now back to the regular slides, but you can feel free to peruse this and research black holes. So here's what I promised about the implication of the time warping of gravity. Remember this formula: the total interval in space-time is the speed of light multiplied by the time. It should be c squared times t squared. I made an error in my math. C squared times t squared minus the interval in space, x squared. So again, that tremendous factor of the speed of light multiplied by the interval in time. And here's a couple of headlines from when Eddington did his experiment and validated Einstein's theory. This is the moment when Einstein became the most famous scientist in the world, was when he overthrew Newton demonstrably by the results of this experiment. Okay, here's the really cool thing. Most of the effects of gravity you feel, the reason that your feet are stuck to the ground, is because clocks at ground level run slightly slower than clocks at the top of your head. The warping of space and time is such that it causes clocks to run slower when gravity is strong, when the warping of space-time is significant enough, or has any significance as a little warp. It also has the same effect on distance measurements. If you were to lay a meter stick out at your feet horizontally and then lift that meter stick up to your head and measure it horizontally, there's a difference in those meter sticks. But the difference is absolutely minuscule. It cannot be measured by any experimental apparatus known to humanity, and probably no apparatus we could ever devise. But that same tiny, tiny deviation in the measurement of lengths is also attributed to the measurement of clock rates. And then you have to multiply that measurement by the speed of light, which is a really big number. And the implication of that is that most of the effects of gravity we feel are because of time warping, not because of space warping in the theory of general relativity. So the force of gravity for any object is mostly due to the warping of time. There is an equal amount of warping of space, but that doesn't have as many implications for our measurements of intervals or trajectories through space-time. Okay, gravitational redshift. Remember I said that clocks move more slowly when near a gravitating object. Mike, can you keep me a little bit apprised about the time? We got about
15 minutes.
15 or 20 minutes left, all right? So if you have some hot particle that's hot enough, or collection of matter that's hot enough that it's glowing, like, I don't know, the surface of a star, the surface of the sun has gravity that's higher than the gravity we experience on Earth. And so the clocks on the surface of the sun are running that much more slowly than the clocks on Earth. Well, as an electrically charged particle is implicated in the emission of a light wave, the light wave measured in the frame of reference right near a strongly gravitating object, the length scale and the time it takes to measure out a wavelength of light, those are stretched near a gravitating object. So when we look at light from things that are deep inside a gravitational well, what's called a gravitational well, remember that divot? We see that light what is called redshifted. Now, it wasn't that red light necessarily was emitted by that object. The surface of the sun, you can't actually, it's really hard to measure any appreciable gravitational redshift from our sun, so I'm exaggerating this for effect. I hope you can forgive me. But it's as if blue light were emitted at the surface of a really massive star, maybe a white dwarf or a neutron star. And by the time it gets to your eye, instead of being blue, it's greenish or yellowish. Because you exist in a different reference frame than the reference frame where that light was emitted. Where that light was emitted, relative to you, the clocks are running more slowly, lengths are a little expanded. So a blue photon is a blue photon, but when you receive it in a different reference frame. So you may have heard or read or seen on a science show this idea that stretching space-time stretches out photons. That's wrong. Stretching space-time doesn't stretch out photons. A photon is generated instantaneously in a local parcel of space-time, and it's generated in a way that's consistent with the rulers and clocks and electrodynamic forces that exist in its space-time. And when you measure it, you're in some other inertial reference frame or near inertial reference frame. So it's the difference between the reference frame where it was emitted and the reference frame where you exist that explains it. The photon doesn't lose any energy crawling out of a black hole or near a black hole. Photons don't have to huff and puff to get away from a gravitational field. A photon's a photon, and it always travels at the speed of light. It's carrying to us messages about the relative differences in the geometry of space-time the warping of space-time between where we are now and here and where the photon was generated. It's a subtle difference, but I think pretty cool. And we can apply this to cosmological scales as well. You've heard about the expansion of the universe. And once again, you will read erroneously. Now, I don't have a PhD in physics, but I try my best to understand the best knowledge that people have about these phenomena. And Nobel Prize-winning physicists who've written books about cosmology and whatnot, and even Einstein himself. I was reading through some collected papers of Einstein archived at Princeton University, and I saw Einstein himself corroborating what I'm about to say. Light is not stretched as it travels through space-time. It's because we're comparing our local reference frame to the local frame where that photon was generated that we see a difference. Otherwise, you get all these crazy questions like, if photons are stretched out and lose energy as they travel through space because they're shifted towards the red, lower energy end of the spectrum, where does that energy go? Is it radiated away as gluons or neutrinos or other photons? Well, it doesn't go anywhere. Photons don't lose energy coming in and out of gravitational fields or other warped space, such as the expanding space of the universe. It's because we're measuring the relative reference frames of something that's distant in space and time compared to ours. And this even applies to the Big Bang. You've seen these images, or some similar images about space expanding cosmologically, the expanding universe, and as the universe expands, photons within the universe, that's these wiggly lines on these balloons, the photons expand. Again, that's not the best way to think about it if you want to have an accurate view of the way reality works. The photons aren't expanding, it's because the photons that were emitted billions of years ago existed in a different reference frame than the reference frame we inhabit now, billions of years later. That's where the difference comes from. They're not losing energy. They're not petering out as they travel through space. And yet, when we look at a distant galaxy, here's an image of distant galaxies, you can see these red splotches. These are galaxies so distant that the visible light has been stretched into deep red colors. And this is because of the expansion of space. And it's comparing our reference frame today to the reference frame of that galaxy located billions of light years away in space and billions of years away in time when the universe was smaller. Now, this is another mind-blowing thing. You look out at the night sky and you expect a bigger and bigger universe as you look further and further away. But actually, as you look out into the universe, you're seeing a universe that was smaller. Remember, the Big Bang began as a tight, compact collection of matter and energy that expanded. We know the universe has expanded for billions of years. So when you're looking at billions of light years back in time, you're looking at the surface of a smaller universe. Pop! Right? These are some of the implications of general relativity that are hard to wrap your mind around, but beautiful to understand and conceive of. Another thing that happens with cosmological objects is something called gravitational lensing. This is called an Einstein ring. The Hubble Space Telescope has viewed this orange dot surrounded by this blue halo. The orange dot is a galaxy that's close to us, and that blue halo is a galaxy directly behind this red dot that is billions of light years further away. The light is bent around that galaxy and magnified so that we can see its image smeared out around that foreground galaxy. And scientists have used these properties of gravity in order to literally create a telescope into things far distant in the universe, things that we would have trouble or it would be impossible for us to otherwise see. Here's gravitational lensing in a cluster of galaxies. If you look closely, you can see kind of a Cheshire cat smile. Well, those big blue arcs are distant galaxies whose images have been amplified or magnified and distorted by the intervening mass. And this is one of the ways we know dark matter exists, because if you try to calculate the total amount of matter required to make this lensing effect, you end up with needing more matter than you can see visibly emitting hot radiation. And that's where dark matter comes from, is this idea that, well, one of the reasons is that we see the effects of this matter. And then this is gorgeous. This is called an Einstein Cross. This is an image of a distant quasar, very distant quasar, magnified and amplified by a galaxy in the foreground that's kind of lens-shaped. So instead of making a ring, see what it does? It's called an Einstein Cross. And all of these are the result of calculations only available to us. The model of the way the universe works is only consistent so far with Einstein's theory of general relativity and the warping of space and time. Here's Einstein's equation. This part explains the geometry of space. Those mu and nu Greek subscripts have to do with the fact that you need to combine the effect of space and time. Those subscripts run from 0. So you can think of Euclidean three-dimensional geometry as x1, x2, and x3 instead of x, y, z, right? In Einstein's four-dimensional geometry, it's x0, x1, x2, x3. And x0 corresponds to the unit or the axes of time. While these subscripts, mu and nu, correspond to the 0, 1, 2, 3, 0, 1, 2, 3, and has to do with the way you formulate the equations when you write them down. So the curvature or the geometry of space, dependent upon the warping of space and time together, is dictated by the amount of energy and matter in a region of space. And then there's this extra term, this lambda term in the middle. That's the cosmological constant. So when Einstein first, this decomposes into 16 different coupled equations, and it's impossible to solve this by writing down symbols on a piece of paper, except in a few very special situations like an isolated mass, an isolated black hole, an isolated perfectly spherical mass. Even for a system as simple as two particles orbiting one another, you can't solve Einstein's equations analytically. You have to simulate them. But that being said, when Einstein first came up with these equations, he recognized that this part of the equations implied that the universe must be either as a whole expanding or contracting. It couldn't be static. Well, at the time Einstein lived and did this work, they thought that the Milky Way was the only galaxy. They had no idea about the scale of space, much less the extent of space-time. So he thought that to be consistent with what science knew, what astronomers knew, he had to introduce this fudge factor that kept the universe from expanding or contracting, that allowed the universe to just be static. Well, if he had kept this fudge factor in and allowed it to take on different variables instead of just canceling out what his other parts of his equation said, Einstein could have predicted the expansion of the universe a decade or so before it was discovered by people using telescopes. So Einstein's equation is so powerful that it contained insights about nature that were missed for centuries of observation. And if you want to know more about this, there's this wonderful YouTube video. Again, you can pause this video and check that out. Just a couple more slides. Another implication of Einstein's equations is the existence of ripples in space-time that propagate out at the speed of light. We call these gravity waves. So Einstein predicted gravity waves in the 1920s, but they weren't observed until about 2012 or so. It took nearly 100 years. They're so feeble and faint that they were very difficult to detect.
And needed very, very sensitive instrumentation to be able to do it.
Right.
and corroborate that it actually measured what it measured.
Right, instead of a passing semi-truck or whatnot. So they built these gravity detectors in very different parts of the planet.
It's LIGO.
Yeah, LIGO. All right, so what are some of the implications for general relativity about what we know of our cosmos? Here's the sun and some planets and a comet, and if you start zooming out, now this is kind of a logarithmic plot, so every time the picture moves by a few pixels, it's 10 times further, and then 10 times further, and then 10 times further. You get to the boundary of our galaxy, and then you get to the cosmic microwave background radiation, which is the perimeter of this artistic drawing. So that can be thought of as a kind of cosmic horizon. Remember, we see the 13.78 billion year ago cosmic microwave background. I may be off by a decimal or two. But you see that, and that's actually the surface of a smaller universe, of our universe when it was smaller. And we can think about all of the stuff that was generated during the Big Bang, 13.8 billion years ago. Where is it today? So we can see this optical horizon. This should be called the optical horizon. I mislabeled this. It's not the particle horizon. The optical horizon is about 13.8 billion years. That's how far back we can see in space. But if you were moving along with that material in the intervening 13.8 billion years, it's 46 billion light years away. So in another sense, this is the edge of the universe. But it gets even more complicated because of relativity. There's this notion of a Hubble sphere. And that's this sphere centered on our point of view. It could be centered on any point of view, anywhere in the universe, but we only live here. We only have our relative reference frame with which to compare others. There's this Hubble sphere centered on our point of view that's about 14.4 billion light years. This is the transition point where objects moving through space-time or carried along with space-time as the universe expands. Once they reach this boundary, the light they're producing can never reach us. So the edge of the universe, 46 billion light years away, the light that those things are emitting today will never reach us. We will never see it if we waited trillions of years. It's beyond a cosmic horizon because of the expansion of space. And the cosmological event horizon is a little bigger than that because the Hubble parameter is changing over time. You've heard about the accelerating expansion of the universe. Well, that adjusts this 14 billion year sphere to something like 16 billion years. Light years away. So anything that's further away than 16 billion light years today will never be seen by us. And in fact, the cosmic horizon will shrink over time to the point where eventually our sky will go dark because the universe, the rate of expansion is increasing. And other than our local universe, so it won't completely go dark, the Andromeda galaxy and some of the other nearby galaxies will still be there. But if there were an intelligent species that lived 100 billion years from now, they would never be able to detect the cosmic microwave background. They would never be able to detect anything other than the nearest other galaxies. Their presumption might be that they live in a tiny universe because the universe is expanding and carrying galaxies away over the cosmic horizon. And these are all implications of the theory of general relativity. And if I move the universe out of the way a little bit, I can give you some references to look up to see more information if you're intrigued by these topics. I recommend that you look up some of this information. And one final slide. This is a picture of a forest from above. And there's this notion of a reachable horizon. So imagine you're in a forest and you look around and the trees that you can see nearby are relatively few because of the obscured line of sight. You might be able to see 9 trees. And then as you walk further in the forest and do a survey of the total number of trees. Maybe you see 38 trees, and then you walk the same distance further and you see more trees and more trees. Well, the same kind of thing is relevant to the universe. The further away we look in space, we can expect to see ever more total or cumulative numbers of galaxies, right? Each shell of distance, each additional million light years or billion light years away, you might expect to see more and more galaxies. This falls off a bit near the Big Bang because galaxies hadn't formed yet, and that's one of the things the Webb telescope is going to help us peer into, is the earliest epoch of the universe. But in general, you would expect more and more galaxies as you move further and further away. Now, here's the weird thing. The reachable universe, if you were to set out in a spaceship that travels near the speed of light today, away you go. You could reach about 3% of the known galaxies in the universe. Even moving at the speed of light, they'd be carried away from you by the expansion of space-time faster than your ship could go. You would never catch up to 97% of all the galaxies in the universe. But one should be enough. We've got 100 billion or so stars and 100 billion or so planets and a lot of exploring to do. And that's what I have to say about general relativity.
That's great. Thank you. Well, it's a stunning topic. It's very hard to comprehend all the implications and the attitudes of it. I thought, I don't know if there's any questions from the audience. I had a couple of thoughts.
Okay, go right ahead.
Any ideas, any thoughts out there?
You'd have to repeat them here.
Right. Okay. To me, yes?
I have a question, but it's about dark matter.
A question about dark matter, okay?
So I'm just curious, Scott, if you know if there's anything being developed to be able to see it.
Is there anything being developed to be able to see dark matter? Well, yeah, that's a great question, and the answer would be very deep and require, an exhaustive answer would require a couple of Science Sundays, but very quickly, telescopes have spotted the evidence of dark matter because of its implications for gravity, the gravitational effect. So there is very, very confident belief, or very confident evidence that allows scientists, a lot of evidence that allows scientists to be confident that dark matter exists. And that evidence is cosmological. It's about the effects of dark matter on things the size of galaxies and galaxy clusters and the gravitational warping it causes and whatnot. But what is completely unknown at this juncture is, what the heck is it? When was it generated during the history of the universe? How does it relate to other particles and forces that we know about? None of those questions has anything other than a speculative answer at this juncture. There are all kinds of experiments underway to look for hypothesized candidates for dark matter, from things like sterile neutrinos and axions and these particles. So almost every physicist, if not all of them who explore this question, believe that dark matter in its most granular form takes the form of fundamental particles of some sort. But nobody knows what those particles are, how they got generated, when they got generated in the history of the universe and the Big Bang, etc. So lots of studies underway about that, but no satisfying conclusions yet. And by the way, that lambda, the cosmological constant that explains the expansion of space or accounts for the expansion of space, that's called dark energy. And that's energy inherent to the fabric of space-time itself. Like, this is a really poor analogy, but to give you a sense of it, when you stretch a rubber sheet, there's elastic forces, there's energy stored in that. Well, as the cosmos expands, there's more and more energy in the expanded cosmos over time, and that's dark energy.
Creating energy.
It's energy inherent to the properties of space-time. So as the universe expands, there's more and more space-time according to our metric, our measurement of the amount of space-time. The amount increases, so the amount of energy would increase.
But that flies in the face of energy cannot be created or destroyed. Just the growth of
Right.
the universe is causing more energy inherent in the universe.
Great point. And I didn't really want to talk about this because this is probably going to cause some people to cry. But the conservation of energy is not true if you start looking at general relativity and comparing reference frames that are vastly different, inertial reference frames. So just like a photon seems to lose energy as it goes from a gravitational well to us, the universe seems not to conserve energy on cosmological scales. In fact, the very notion of the conservation of energy and the relationship to what I've mentioned before, Noether's theorem about continuous symmetries implying that there's a conserved quantity, all of that breaks once you start dealing with the equations for the universe as a whole. So you can think of it as a loophole in the law of conservation of energy, just like
I was thinking of it as a loophole.
Yeah, in quantum mechanics, there's a loophole in the uncertainty principle for the conservation of energy. So at the smallest scale and the largest scales, the conservation of energy does not have to be strictly adhered to.
Last question. Thinking of what I was talking about with the James Webb Telescope and looking back, so you're looking back in space, you're looking back in time, I found it very difficult to explain to my son-in-law or other people or to myself. If you're seeing a planet, or if you're seeing a star that's 14 or 13 billion years old, you should be, or the light from it emanated 13 billion years ago, you're seeing it very close to the beginning of the universe. I can understand, the sun is 8 minutes away, much farther away,
Right.
objects are going to be there. But you're also looking back in time, so you're seeing something that emanated at that time. When it emanated, we were very close to that.
Yes.
Why don't we see it? Why didn't we see it all along? Or what are we actually seeing? And if it went for a time, why don't, I get confused about how to say we were in a different place in space-time
Yeah.
when that light emanated, and why are we seeing it now, and why didn't we see it at any other time?
Yeah. So, you know about the cosmic microwave background. Remember what I said about the universe was actually smaller in the past compared to today? At the point in time when the cosmic microwave background radiation was emitted, the universe was about 40 million light years in extent.
And we'd have been part of it almost.
And we would have been part of it.
Right.
So if the Earth had existed and we or our ancestors had existed 12 billion light years ago, 12 billion years ago, the sky they would see would be much more densely packed than the sky we see now. And distant things would not be nearly as redshifted, right? Because the point of view of the inertial reference frame of the most distant observable universe back then would be much different than the reference frame we occupy now. It's the comparison of reference frames that matter. If we had been in that baby universe and smushed more closely together with what we now consider the most distant galaxies in the universe, if we had been closer to them, and we were billions of years ago, we would have seen them as different. We would have seen them as baby galaxies with blue stars. But here we are billions of years later, and the light has taken billions of years to reach us. And in the interim, our local space-time has been carried along by the expansion of the universe. So our local space-time here and now is a very different reference frame than it would have been billions of years ago, wherever we would have been located, the parcel of space-time that contains the Earth. So it's the comparison between then and now. And if you'd run the clock backwards super fast, 1 billion years an hour, 14 hours back, you would see the distant universe, instead of getting redder and redder, you'd see it getting bluer and bluer, and the cosmic horizon getting smaller and smaller. And it's the implication of the expansion of the universe that helps us understand the difference in what we would see then compared to now. So yeah, if we were back then, back there in space and time, we would see things very differently.
But we're looking back in time. We're looking to how it was 14 billion years ago.
Yeah, but we're looking at it from our perspective in space-time. That's the point, right? We're looking at it, and we can't help but see that distant place in space-time from our perspective now, with the universe, the scale of the universe with its ticking clocks and meter sticks. The only scale we have available to us to measure these things are the scale here on Earth, now. And it's when we compare that scale to now that we see a big difference. But if we could march back in time, our meter stick would still be a meter stick, and our clocks would still tick at 1 second per second. We wouldn't see any local change. But what we would see in the surrounding universe would change because there's less difference between our reference frame and the reference frame then as we get closer to then.
It's a challenge to visualize.
And
I'm just imagining, I'm putting it in this picture in my mind, and I'm trying to maybe anthropomorphize it to understand it. Let's say that you can look back 14 billion years in time, and you could see this star, and you could even see this planet. And on this planet, maybe a woman has left 50 of her kids out to go play, right? And
Okay.
they run out there. And if you could look back in time, you'd see that right before she let them out to play. You'd see everything collapsed in and close, just like you'd see the whole universe in collapsed and close, not all run out and play, not all spread out and so on, right?
Well, so a meter to her would be a meter. A second to her would be a second. But comparing that to our second, by observing it through a telescope, we would see her second being longer, and we would see her meter being shorter. Is that right? I think so. So if we had a powerful telescope to look at an alien with her brood of alien babies, as they existed billions of years and billions of light years ago, we would see them moving at a different speed with different energy, because our scale for measuring speed and distance and energy and time, our scale is different. But if humans had evolved 10 billion years ago, such that we were in a smaller cosmos and closer to that nice alien family, then we would see them frolicking at a more rapid pace, because the energy, the time scale, the distance scales would be, our scale would more closely resemble theirs. So it's the difference between our point of view, our local. You can only ever exist locally. This is one of the implications of Einstein's relativity, is that every interaction, every observation can only ever be local. So anytime you start talking about something appreciably distant in space and time, you have to start taking into account the geometry of space-time. And one final thing, the overall geometry of our universe, if you neglect the tiny little ripples due to galaxies and stars and black holes, the overall profile of the geometry of our universe seems to be flat. We don't live in a universe with curved geometry on the largest scale, which is another mystery in physics that has some plausible explanations and whatnot. So, amazing stuff.
Yeah, fascinating. All right, well, thanks so much.
All right. In a month, my intention is for Mike and I, what I'd like to do with my time is for you and I to have another powwow to talk about, why does science education matter? Why does science matter? What benefit is it? Why do we like it? Why do we do it? That kind of thing. So.
Okay, great.
All right, see you.
See us in 2 weeks, and have a great end of March and April, and the weather's nice. Get outside.
All right.
Great. Thanks so much.